Hello everyone, I'm Jung from Purdue University. In this talk, I'm going to present PMEM-Spec persistent memory speculation. This work is done with myself and Dr. Chang Jung at Purdue University. So let's get started. So I will be talking about persistency models, which defines persist order for failure recovery. Like memory consistency, strict persistency is intuitive but very slow. And the more you relax constraints, the better performance you will have. Meaning that relaxed persistency in general outperform strict persistency. However, relaxing constraint increases programming difficulty, since programmers should annotate their programs. In this paper, we tackle this presumption that relaxed one is always better than strict one. To this end, we present persistent memory speculation, that is hardware-software co-design for strict persistency. This is the first demonstration of strict persistency outperforming relaxed one, with significantly improving performance. This is the executive summary of the talk, and let me start with the background. Persistent memory is here. It is available in the market. This technology allows user space application to access non-volatile memory with load store instruction. And it also enables recoverable application with durable data structure. Although it is promising technology, it is not pre-launch. Here are some challenges in PM programming. In particular, you must be careful when updating data in PM, meaning that persistent memory stores must be atomic and ordered. First, to make your PM store atomic, there are existing techniques such as write-ahead logging or shadow paging or idempotent processing. These techniques guarantees PM stores in a given failure atomic section executed all or nothing. On top of atomicity, PM stores also must be ordered using cache flush and store fence instruction. This is also known as persist order. The reason why it requires flush and fence is that data only becomes durable when it reaches to persistent domain, which include persistent memory controllers and PM itself. Therefore, PM stores must be flushed from caches, and these flushes must be ordered. So in this paper, we target this property, and let me revisit the prior first and see how they manage persist order. The first approach is strict persistency. Suppose that your program executes the following store instruction for log AB and data AB. Strict persistency guarantees PM stores arrive to the persistent domain one by one in the program order, by placing flush and fence instruction for each store. Therefore, this model basically uses caches as write-through, so you can imagine how slow it will be. Here, we do not see any memory level parallelism. But the good thing about strict persistency is that it does not have to change the program. The compiler or library can easily deal with inserting flush and fence without programmer intervention. As you can see, this model is intuitive to use, but very slow. So we often relax some constraint, leading to relaxed persistency. This model allows reordering within usually delineated failure atomic section so that it can reduce the number of fences and flushes. So your program will be partitioned into epoch, and instead of placing flush and fence for every store, we do them at the granularity of epochs. This way, it significantly increases PM write throughput. Now, fence instruction deals with multiple cache flushes at a time. However, relaxing ordering constraint requires programmer annotation, since it requires understanding of underlying persistency models, architecture, and program behaviors to enforce proper ordering while maximizing performance. This is not what compiler or library can do the best job, so there must be annotation given by programmers. Here, we have a well-known trade-off between strict and relaxed persistency. Strict model is intuitive to use, but slow due to frequent fence instructions, while relaxed persistency is fast but requires programmer intervention. And there are many prior works proposing architecture for relaxed persistency since it can provide better throughput. So let's look at how they provide persist order. The target problem of prior work is to deal with fence overhead. In general, there are two approaches. We can either reduce the cost of fence or reduce the number of fences. To reduce fence cost, they try to hide fence latency to the background by letting the hardware enforce it. Cache flushes are happening outside of the critical path if possible. And to reduce the number of fences in the programs, they further relaxed the persist order constraint, leading to better PM write throughput. Or others propose multiple store passes to PM, slow and fast passes that naturally obviate the need for fence instructions by placing log write to the fast pass. In summary, all prior work have the same goal, which is to reduce fence overhead. Unfortunately, their performance improvements comes at the cost of hardware complexity. The hardware changes are required for supporting intra and inter-thread persist order. For intra-persist order, all prior works added special buffer in the L1 cache called persist buffer that controls the cache flushing order. So these buffers store the cache blocks modified by PM stores and flushes them with the program order. And for inter-thread persist order, which requires to detect inter-thread dependency, they leveraged cache coherence. In particular, they monitored cache coherence messages in the L1 cache, and based on the messages, they can identify inter-thread conflict and order cache flushes between threads. So their hardware extensions are mostly made in the L1 cache side, where they provided the persist order. However, this design decision further complicates the hardware to handle the corner case, which is ordering between L1 cache write-back and PB flush. Since they managed persist orders in the L1 cache, the modified cache block should be flushed through the PB before the L1 write-back. Otherwise, this complicates tracking persist orders, since the block is now in the shared cache. This can result in incorrect persist order. So the prior work presented hardware mechanism for handling this corner case. First, one paper put the special buffers inside of coherence domain, so even if the L1 write-back happens before PB flush, persist buffer still can track dependency. However, this extends the hardware coherence mechanism. The other paper used a sticky bit in LLC to keep tracking of L1 write-back in the shared cache. And it even placed hardware Bloom filter in the persistent memory controller to check pending persist in persist buffers. Bloom filter checking must be performed for every PM read to prevent stale read. However, this approach increases hardware complexity further and increases PM read latency due to Bloom filter checking. And others buffered L1 write-back until the block is flushed from the PBs. So they all need to increase the hardware complexities and incur extra latency to guarantee correctness. However, we wanted to overcome such limitation. In particular, we wanted to minimize hardware complexity while eliminating any delays in accessing PM. So in this paper, we present the PMEM-Spec, persistent memory speculation. We simplify hardware by leaving caches unmodified. The only place PMEM-Spec introduced new architecture is in the PMEM controller. At the same time, like strict persistency, PMEM-Spec does not require programmer annotation. So PMEM-Spec is hardware software co-design for high performance strict persistency. Here, hardware software interaction is the key for high performance without making hardware complicated. Let me tell you 3 key ideas of PMEM-Spec. First, It speculates all PM accesses as they will be correctly ordered, even without any intervention in the core, caches, or by software. We are simply expecting that everything is going to be okay. For this purpose, we propose separate data paths for load and store to persistent memory. Second, PMEM-Spec detect ordering violation, which we call speculation in hardware. And for this purpose, PMEM-Spec leverage architecture compiler interaction. Lastly, it delegates recovery to the software. To do so, PMEM-Spec treats with speculation as a virtual power failure, so that failure atomic software execute failure recovery protocol as it encounters system crashes or power failure. They are key ideas of PMEM-Spec, and let me explain the architecture first. PMEM-Spec has separate data paths for load and store. Here we have persist path, which is FIFO store path to persistent memory, which directly connect the store queue in the core to the PM controller. These passes completely bypass the cache hierarchy, so the PMEM-Spec does not place any modification on caches. When store instruction committed from the store queue, data is written to the caches and to the persist path at the same time. But the data in the persist path updates data in PM, while the dirty cache lines are silently dropped on their eviction. Also, the store path works as FIFO data path. So the PM stores arrived in the store commit order. This simplifies the intra-thread persist order. And for PM load, we have regular data path. And this path only serves read to the LLC. With this unique architecture, PMEM-Spec speculate PM accesses such that they are always correct. So then I will explain what PMEM-Spec speculates. PMEM-Spec speculates both PM load and store. Let's look at load speculation first. This speculation applies to both intra-thread and inter-thread dependency. PMEM-Spec speculates PM load as it always reads latest value from PM. In particular, PMEM-Spec optimistically assumes that prior store request always persists before the following load request. This unique speculation arises in the PMEM-Spec separate load-store data paths. And for store speculation, PMEM-Spec speculate PM stores persist in the correct order. Therefore, it ignores any fancy instruction for PM store. This store speculation is particularly harmful when inter-thread dependency, since there is no ordering guarantees between persist paths. This implies that stores from different cores can persist in any order. On the other hand, intra-thread persist order is easily handled by persist paths. PM stores from a single thread always persist in the store commit order through FIFO persist path. So PMEM-Spec speculate both load and store in the PM controller, as they are benign. And there's nothing like fence or buffers in the CPU or caches. However, PMEM-Spec may encounter ordering violation, which we call misspeculation. Since they speculate both load and store, there are misspeculation for load and store as well. Let me explain load misspeculation first. Load misspeculation causes stale read if the prior stores are pending in the persist path. This problem can occur in separate data paths if they have different latencies. This example illustrates how this is happening. The core executes store A followed by load A. And store A is written to the caches and eventually evicted, but it does not update the data in the PM. Later, load A was executed and it goes all the way down to the persistent memory to fetch data. And it speculates that this fetch is safe, but there is no guarantee that prior stores A arrives at PM before this fetch. And if there is store still on its way to persistent memory, the fetch will fail. and it violates memory consistency. This ordering violation must be detected and recovered. Otherwise, program may produce wrong output. Then how do you detect it? The important observation is that if blocks are in caches, load will never be speculated, since data are served there. For example, load A hit in the caches, it does not go to PM, and the load will always be benign. This observation drives us to monitor recently evicted blocks if they are overwritten by stores in the future. In particular, when the block A is evicted from LLC, PM controller receives eviction, but does not update data. Since the block A is now not in the caches, node A has to fetch data from PM, which PMEM-Spec speculates. Later, when store A appears, at this point, PMEM-Spec can tell the fetch will stay, and it is with speculation. Then the next question is, how long should we monitor these blocks? If this is too long, the number of monitored blocks becomes too many, making monitoring inefficient. If this is too short, stale read can go undetected, crashing programs or causing wrong output. To determine how long the block should be monitored, let's first see how PM stores travel persist passes. Their latencies are fixed in hardware design time based on the hardware specification. Therefore, PM stores must appear between the best case and worst case latency. To leverage this observation, PMEM-Spec monitors evicted blocks until the worst case persist path latency. So this window we call speculation window, and it starts when the dirty block is evicted from LLC. And when the block is fetched by the load and updated by stores sequentially within the window, PMEM-Spec identify the fetch was speculation. Eviction, fetch, and PM store must happen in order. Otherwise, the fetch is benign. So we have discussed load speculation and how to detect with speculation with monitoring for speculation window. This is not only speculation of PMEM-Spec, and let's move on to the next case, which is store with speculation. This can happen when there is inter-thread dependency. In particular, two or more threads access the same address. These stores can persist out of order. For example, two stores execute store to the same address A. And since thread 0 is executed first before thread 1, thread 0 happens before thread 1. If this ordering is not preserved, store can persist out of order. To capture this dynamic ordering, prior work leveraged cache coherence and checked if other thread request an exclusive permission to the cache blocks currently being persisted. However, PMEM-Spec does not see the coherence messages. We made this decision purposely not to complicate cache hardware. The key challenge here is to infer inter-thread store order without cache coherence extension. This is a daunting task since there is no existing hardware component to leverage except cache coherence. So PMEM-Spec receives an ordering information from applications. In particular, PMEM-Spec assumes that programs are data race-free, meaning that all inter-thread dependencies are always delineated by synchronization primitives, such as lock and unlock. In other words, inter-thread dependency always happens inside critical section. Otherwise, programs are not data race-free. Therefore, we can infer inter-thread store order from critical section order. Please note that this assumption is not strong or unrealistic, but it is common in modern programming languages such as C++11. So all we have to do is to deliver critical section order of thread to the hardware. For this purpose, PMEM-Spec uses a speculation ID that is shared by all threads and atomically incremented by thread when they enter the critical section. Since the ID is atomically increased on entering critical section, it captures the precise execution order of critical sections. So if PMEM-Spec observed that lower ID arrives higher IDs, this implies that stores arrive out of order. So it determines it as store misspeculation. And PMEM-Spec introduced new instruction that assign and remove the speculation ID from and to thread. These new instructions are executed within critical section, and since the compiler generates such code during compilation, it does not require programmer annotation. Let me show you examples how PMEM-Spec detects store misspeculation with this technique. This is example of benign stores. So thread 1 starts first. After acquiring a lock, the thread is given the speculation ID 100 with compiler generated code. And store A goes to both caches and persist paths with the speculation ID tag. And we untag the ID when a thread exits the critical section. Please refer to the paper for details if you want to know why we remove it. And thread 1 exits critical section, and thread 0 follows. Similarly, the speculation ID is assigned, but this time the ID is 101, since it increments by entering the critical section. And the store A is tagged with ID 101 and goes to PM. These stores are safe since store happens in increasing order of speculation ID. On the other hand, this is an example of store with speculation. Similarly, thread 1 starts with acquiring a lock and is assigned the speculation ID 100. Then store A executed, but this time the data is experiencing delay in the persist path. This can be happening due to contention in the channels. But persist path operation is speculation, therefore critical section exit without waiting its completion. Then thread 0 get a chance to enter a critical section and execute store A with the ID 101. If this store with ID 101 persists before the stored ID of ID 100 from thread 1, and PMEM-Spec observes the out of order persist with the out of order arrival of speculation IDs. Therefore, PMEM-Spec identifies store speculation and calls for recovery through the software. As mentioned earlier, PMEM-Spec delegates the speculation recovery to the software, mainly relying on failure recovery features of failure atomic software runtime. More specifically, when the PMEM-Spec architecture detects speculation, it generates synthetic power failure. Then the OS captures this hardware interrupt and relays it to the failure atomic runtime. Then the failure atomic runtime executes failure recovery mechanism if they encounter the power failure, so that it aborts and restarts transaction. Since failure atomic runtime provides its own recovery protocol, the speculation recovery can be easily handled by transaction aborts and restarts. So the takeaway is that PMEM-Spec recovers from speculation with recovery protocols of failure atomic software by treating it as virtual power failure. Now I will briefly go over the simulation methodology of PMEM-Spec. I used full system simulation mode of Gen 5 with Linux kernel version 4.8.13 and Ubuntu 16.04 as the OS. Our evaluation used a mix of micro benchmarks and whisper benchmark suite. To compare PMEM-Spec with prior solutions, we implemented the software-based ordering with Intel x86 ISA and TPO and hops. Note that TPO and PMEM-Specs are strict persistency, while others are relaxed persistency. The first evaluation is about throughput, so higher is better. For micro benchmarks, even if PMEM-Spec is strict persistency, it shows similar performance to the hops, which is the state-of-the-art epoch persistency. This is because these benchmarks only contain tiny transactions, so there are less room for speculation. On the other hand, more realistic benchmarks in Whisper benchmark suite, there are clear performance improvements over previous works. That is because they have much larger transactions than micro benchmarks, and PMEM-Spec can augment speculation opportunity without delaying program. The novelty of PMEM-Spec is that it outperforms others with strict persistency and less hardware modification. The next experiment is the persistent path latency. We vary the latency from 20 nanoseconds to 100 nanoseconds for sensitivity analysis. Since the persist path operation is mostly out of critical path, PMEM-Spec always outperforms the baseline, which is epoch persistency of Intel x86. Programs only see its latency at the end of transactions to drain or persist made within transactions. However, this equally applies to hops and other designs. There are more discussion in the paper. For example, you will find the speculation buffer architecture and software support for PMEM-Spec in the paper. Also, the paper has more evaluations such as scalability and sensitivity analysis. Those who are interested, please refer to the paper. This is the conclusion of this talk. This paper presented persistent memory speculation, which is hardware-software co-design for persist order. PMEM-Spec speculates PM excesses in hardware and recovers from this speculation in software. With PMEM-Spec's unique architecture, this speculation turns out to be extremely rare, leading to high performance strict persistency. Our evaluation results show that strict persistency can outperform relaxed persistency with a novel hardware-software interaction. This is the end of my talk. Thank you for watching. And if you have any questions, please join the session 6A, Hardware for Crash Consistency.